maclib or something inside of Wing. Again, like extremely impressive body of work, but it is not one proof. It is a lot of proofs. SEL4 is the high level proof is essentially one enormous proof.
This complicated system satisfies this complicated collection of specifications, which are all combined into one. So now it's one proof instead of 5.
Yeah, more or less. Yeah. The thing is they extract a lot of the code from it, and so the specification is quite large and complex. But from that, they extract. What ends up happening is you extract partly into an intermediate level. They have this like pseudo Haskell intermediate level that they extract from the Isabelle code to, and then they
from that they go to,
and then they go from there to C. Yeah, and so then there's chunks from C that try to they've got proofs of the translation from that intermediate to C, and proofs of the translation from Isabelle to the intermediate, and that's how they construct those things.
How does Isabelle, actually I don't know generally, does Isabelle have like a built-in extraction thing? Like I know Conf has like fairly standard things, but I don't know about, does Isabelle have like standard extraction? Like is this like Haskell-like layer standard thing, or?
Oh no, that's something
one-off?
they've built. And in fact, they have heavily modified Isabelle itself, but a lot of their changes make it into upstream. There is a lot of overlap with like core developers in the Isabelle world and SEL4 when they started, and so while they have drifted a little bit, there is still patches that get sent back and forth all the time. The Isabelle that SEL4 is running on, their proofs through is not like a departed fork. It is more of like a collection of patches and stuff.
I just want to stay so far back.
Huh?
I just want to stay way back.
So have anybody else dealt with family calculus before? A little bit as well. Yeah. In a standalone or just inside of other programming languages like either a functional language or like Python?
I think it was like a very long time ago. I don't remember what it is.
Yeah.
It just kind of sounds familiar.
I think you came up with it in good old Escher-Bach.
Yep. Oh yeah. Oh man, that's been a while since I've read that. Yeah.
Except it was very abstract.
Yeah.
Gödel Escherbach?
Yeah, Gödel Escherbach is a very influential, very nerdy book. I read that one when I was in 8th grade, I think, or 9th grade, maybe it was 9th grade. But it's long enough ago that I would have undoubtedly a different appreciation for today than I did back then. Once again, fighting with latex. Always. So,
pages. That's not a book that's
yeah,
its
it's,
own.
yeah.
Wow.
It's a larger one.
It's, yeah,
But it is,
it's,
it won't work as very well as an audiobook though.
Really? I mean, you have to read it.
There are diagrams and whatnot in there. Yeah, in Gödel Escherbach.
You can flip around in it, like a book
Yeah.
is,
You
it's
should.
Sometimes you're supposed to.
yeah, it's a collection of related topics, and you can kind of like, you know, like one of those Japanese series, like read it in different orders to like get a little different.
Wow.
It's fine.
Read it in different what?
Different orders. Read the chapters.
Oh, order.
Like it doesn't. You don't have to start at page 1 and go to the end. I think there was a time when like all the budding nerds had read that book and David Kahn's The Code Breakers, and like those were like the two defining books.
Sounds awesome.
If you want a copy of the Code Breakers for free, up at the Hackerspace, like there's a pile of free books from one of the guys who's like cleaning out some storage units and stuff.
Oh, wow.
And there's a copy of it in there.
Oh, that's cool.
Not about nabbing it, but I have one.
Yeah. That's great. Man, I want a hackerspace like that down in San Marcos.
You should look at starting one.
Sounds like fun.
Like if you're, I don't know, if you could try to see if the university could kind of sponsor it in some way with like, you know, a free space or something, but that inevitably comes with more organizational overhead for you, since you have to like justify it every semester or year to the university and say, oh, we did this and had an event for like prospective students and all that stuff. So. think, it's a mistake to try to start something like that by yourself, though. You wanna have a group of other people who are kind of dedicated and spread the load. If it's like one person's like mission, then at some point you'll like get a job somewhere else, whatever, something like will happen, and then we'll just move some.
Well, there's a way like, some I think like in San Antonio, no? Or do you, like, you don't consider like geekdom a hackerspace?
Yeah, I do.
Have you been to TXRX in Houston?
They are definitely, they're
That
so,
one is pretty cool, I've been to that one.
they're so big. I mean, they're definitely also a makerspace and fill a lot of other roles.
TXRX?
Yeah.
Yeah.
But I think within it, like there's sort of a traditional group of hackerspace-esque people. And it's like super,
Is the TXRX, they have like a whole warehouse, and they even have like equipment to like paint like, you know, like car doors and things like that, so they have like literally everything.
it's like more than a city block in the West District.
That's crazy.
Wait, where's that?
Houston.
Oh.
They have a-
TXRX?
Yeah, it's a real warehouse district, like ours used to be before it got rebuilt, and that, you know, the streets and the sidewalks and the floors of the buildings are all exactly the same level, so that you can drive a
really?
forklift anywhere, from any warehouse to any other warehouse.
Wow.
It's like the defining property of a warehouse district for a while. That also means it floods instantly with something, right, because it's like flat, and it takes forever for the water to drain, but, yeah.
But if it gets flooded,
Yeah, it does, it will flood.
but don't they have, you know, like the drains or whatever, if they have the drains, even if it's flat, it's not supposed to flood, right?
That's the theory, but you know, if like 3 inches of water comes down and bam, it just doesn't start going sideways and fit down the drain like this will hit me.
But it's like not a new thing in Houston, like how could they have thought about it before like they built the warehouse district?
I think it was probably flooding when they built the warehouse district. It's like whatever, stack extra pallets, funded. Like originally, most of those, there's still warehouses there that like.
But do you know it actually floods, like TXR, do they actually, like, do they literally like shut down for like several weeks after it floods, or like what happened?
No, they're like, all the buildings there, like all the electricity is like just high on the wall. And if you go in there, like their lasers and stuff are kind of on an improvised floor made out of pallets, that's like an extra couple inches. I think that's enough to.
So they just say like it's gonna flood and we're just gonna be slightly above the flood.
Yeah, and like all the buildings that were finished at some point have like sills. Like sometimes, like considerably away from the building and the sidewalk is basically like a permanent rim of sandbags or something, but I don't think TXRX has that.
Doesn't
Yeah,
that
but
break,
the
doesn't that
space-
break the ability to drive your forklifts everywhere?
Yes, that's why
Okay.
forklift ability is preferred over staying dry all the time. Like for a true warehouse district, right? But nowadays, like. we
But you
don't
could
use-
have like slight inclination, like it's not gonna affect forklift, but it's gonna affect like how the water does. flows, right?
Yeah, you could. I think Houston's.
I mean, that would only make sense, right?
Houston's natural topography didn't help with that.
Houston's
Put,
what?
like, use a little bit of extra space and put a deep drainage canal somewhere, right?
I mean, it has, like grates in the streets and stuff.
Mm-hmm.
There's obviously a storm drain underneath it.
Yeah.
But when it all comes at once, it's like not enough. If it all comes at once somewhere else, then water fountains out of the drains.
Mm.
Right. I've seen videos of that happening like downtown Austin.
But, I mean, it's gotten more built up. For a long time, a lot of those warehouses like had minimal electricity, like electricity in one corner and maybe lights in the building. And they were super cheap, and so like as TXRX grew, they like just kept renting more space and expanding. I guess the modern equivalent is these Amazon warehouses made out of the tilt-up concrete thing that are like a quarter mile by half mile and like huge.
Well, but they have roof, and I imagine like they might as well have like a moat around it to prevent that issue if that's an issue in the area that it's in, right?
Yeah, so that's all, that's all enclosed. Generally has some sort of rudimentary, climate control. It was mainly just to like,
But I think also I've heard that like a lot of those are houses that don't actually have like air conditioning inside. I think like CompCert doesn't have air conditioning either, right?
that's right, only like the
In the
enclosed
area.
rooms have their own one.
Yeah.
Yeah, and most of it doesn't. And, like the big Amazon warehouses, the AC is mainly sort of purpose of dehumidification. Like it's still really hot in there, and when they're that big, you know, they, if a bunch of water comes out, like you still have to control where that water goes. So they have interior roof drains, so you have this like big pipe coming down from the roof into storm drains underneath the
Oh
building.
yeah, I think like when it was really raining hard here, we could hear it here, like, I don't remember if it was just be that
Yeah,
one here.
running through
It
the
was just
wall,
be that, right? Yeah.
running through the walls and down, yeah. Cause if you had to get it all to the edge of the roof, then like cool, and if the roof is too flat, and like there's some leaves or a bird's nest or something that plugs a few of those holes, what happens is the water builds up in one spot, and the roof bends down just a little bit, so that all the water then rushes to that spot, and then it,
Oh.
and then it fails.
Is CompCert, are they still around?
I think so. I mean, they're
Are we streaming now?
a very large,
The lights are red. I think so.
Well, it was red too soon.
Yeah, before you got here, she was here and we told her to start at 7, I don't know what time it is.
Okay, yeah, we're streaming.
Yay.
Oh, we've been streaming like all along, or what was it?
Well, I think when that thing is streaming doesn't necessarily mean when it's hooked up, so they've got some control stuff on there, I think.
Right.
So, yeah, let's go ahead and get started then. All right. Well, welcome to the Austin Formal Methods user group for this month. Woo! Smaller than I was expecting it to be. Yes. That's weird. First of all, we need to thank our sponsors, Capital Factory. Thanks for letting us have this space. If you're interested in getting a membership here or whatever, go ahead and check it out or contact us. We can get you in touch with the folks here. Also, Zulip, they give us a free space to chat. If you're not in the Zulip, just let Rob or I know. We can get you. We've both got admin access. I think Silas, you might have admin access. I don't remember. We'll check. So just contact one of the regulars and we'll get you access for them. And as a reminder, the definition that we are working on for formal methods is that formal methods are techniques and tools which use rigorous mathematical logic to design, analyze, and verify systems with provable properties like correctness, reliability, and security. So today we're going to talk about the lambda calculus. So first we're just going to give a rough overview of what the lambda calculus is. Taking directly from Wikipedia, the lambda calculus is a formal system for expressing computation based on function abstraction and application using variable binding and substitution. So we'll get into what each of those pieces means here in a minute, but today we are going to be focusing primarily on the untyped lambda calculus, but towards the end we're going to briefly touch on the simply typed lambda calculus. So part of where this comes in is functional programming. So the lambda calculus is kind of the origin of the functional programming paradigm. Pretty much all of the functional programming languages can trace their roots back directly to lambda calculus, whether that's a Lisp or an ML or the Haskell, or pretty much any functional programming language is going to have its roots in here. And even ideas from the lambda calculus that are in functional programming have sometimes leaked out into other types of programming as well. So the idea of passing in a function as an argument is not uncommon in like a procedural programming language. You could have closures, which maybe you can see in a procedural language, but I would say that's more common. You would see a notion like that in an object-oriented programming language. That's in a sense kind of what object-oriented programming languages are trying to achieve in the first place. You've also got the notion of a lack of, yeah, what's up?
Oh, I just kind of have a question comment, like, I think I've noticed some people, they call like some procedural languages which allow you to pass like a function, they call it functional, which doesn't seem right, but at the same time I couldn't like really disprove that. Like, do you have any sort of comment on that?
Yeah, so, I mean, I wouldn't call it a functional language, that's just a feature that was originally found in a functional programming language, namely
Right.
the lambda calculus. I think it's definitely one of those, you know, one true Scotsman thing, you know, like what does it make for a true functional programming language? That is a feature which is nice from lambda calculus, which is, you know, the only true functional programming language, I suppose you could say, you know, the real one, the OG. And it is a feature that it prominently had, and so to that extent, maybe you could say it's a functional thing, but I would not call that a functional thing. It's just a feature which is nice from lambda calculus, which a language like C happens to have.
Right, I agree, yeah.
I think that made more sense before Java had lambdas.
Yeah, well, I think
Like that's when I remember hearing it. It was like, oh yeah, you know, first class functions. Once you have first class functions, then it's a functional language.
Yeah.
But then Java had it, and we're like, oh yeah, actually, we want more than that.
Yeah.
It's one bridge we won't cross.
Well,
I think like the
it's-
idea is that like you're not supposed to be able to like change the variables, so like there's not supposed to be variables.
Well, almost all functional languages like do allow you to do that though. Like Haskell.
I don't think Erlang doesn't let you change like the
Yeah,
the
talk
existing
about
thing.
side
Lisp
effects.
does. Right? Lisp quite famously does.
Okay.
Even the purer ones.
Yeah, side effects and whatnot. Yeah.
No.
And OCaml is pretty happy to allow various side effects.
Yeah. Yeah, so it's even object-oriented programming in a certain sense, you could frame that in terms of it's all about closures. That's what all of object-oriented programming is composing closures that we will use later. Go makes that a little more explicit than a regular object-oriented language, where it's like, no, like all it is a data type with a magical function that we have attached to it. That's all it is. There's no ambiguity about which thing owns what. But yeah, anyways, all of these common ideas that we would see inside the functional programming languages originated in lambda calculus. But there is one feature which most of the functional programming languages have abandoned, which is the idea that there are only functions, and that's kind of as far as I know, that's kind of unique to lambda calculus. There is nothing but functions. There is no other data type than functions.
That was a real mind blower when I was going through it, but I was just like,
Yeah.
there's three, it's this function.
It is.
But no, I'm not applying the function. It's like, no, because like anytime you're using tree, it's effectively like do something, and it kind of abstracts that way.
Yeah,
Feel
well, it could be
philosophical.
do something, or maybe you're just, you know, using tree as an item, but like the distinction between these two things is not important, and that's the weird idea. So yeah, we'll get some more of that in a minute, but yeah, most functional programming languages don't literally only have functions these days, but that is, whatever else we might say, lambda calculus is definitely a functional programming language, because that's the only thing that it is. Like, there is nothing but functions. There is no data, there is only functions. And we'll get to that in a minute. So who came up with this weird thing? Alonzo Church. So Alonzo Church was this mathematician. At the time, he was at Princeton, and one of the things that he was trying to do when he was creating the lambda calculus was explore some of these foundational mathematics ideas that kind of got brought up by Gödel. So Gödel came up with the incompleteness theorems, and but the techniques that he used to come up with the incompleteness theorems were a little bit strange to mathematicians at the time. I don't know programmers, but mathematicians at the time. It was kind of a strange concept where you had all axioms were kind of like prime numbers, and that theorems were like composite numbers, and so that if you wanted to have complex axioms in Gödel's construction that involved having different axioms that were put together in certain patterns, it was kind of an odd conception for a lot of mathematicians to accept at the time, and it wasn't clear. You know, it seemed like it was somehow very important, but it wasn't necessarily immediately clear to everybody after his, like, whatever it was, like 1931 paper, that it took a while for the math world to kind of wrap their heads collectively around what the heck was happening here. And one of the specific areas was this, Hilbert had created this Entscheidungs problem. So this like decidability problem. It's, we'll cover a little bit more here in a minute, but that was one of the things that Alonzo Church was creating the lambda calculus to try to explore. But it's worth pointing out that Church has had a significant impact on computer science, especially through his, not only through the lambda calculus and his first order things that he did, but also through his very significant students like Turing and Kleene, Rosser, Rabin. You know, he had quite a list of PhD students. So this Entscheidungs problem that Hilbert kind of described, essentially what they were trying to get at, it turns out there's a lot of different problems which are equivalent to that, but the main kind of goal that they were going for is the idea that there would be a machine that you could take formal logic, you know, a lot of stuff that we talked about in this group, and that from that you would be able to deduce all mathematical truths. Maybe it would take infinitely long or something like that, but in a sense you would be able to find all mathematical truths. And Gödel's incompleteness theorem, it kind of seemed like it may have something to do with that. Like, it seemed like maybe it was saying that that was impossible, but it wasn't really clear to everybody. And so the question was, can you describe the Entscheidungs problem more directly, or something that we know to be equivalent to that problem, and then show that that's impossible, rather than just kind of vaguely saying that this stuff that Gödel did, which is kind of several degrees separated from the problem as described. Are they actually saying that it's impossible, or is this some weird edge case that doesn't really matter, or maybe we just have like a special exception for, you know, under special circumstances or something. So Alonzo Church actually ended the debate. With the lambda calculus, he proved that it was impossible to create a machine which could show the equivalence of two lambda calculus terms in general. It's worth pointing out that I mean the untyped lambda calculus. We'll get to that later. So you cannot show the equivalence of two arbitrary lambda calculus terms, and that was the first definitive proof that the Entscheidungs problem is impossible. You cannot create this machine which will know all possible truths. Around the same time that Alonzo Church came up with that, within just a few months later, Alan Turing created his paper about the halting problem. It was kind of independent. This was before Alan Turing was Church's PhD student. And then so they published within a few months of each other. So after Turing published the halting problem, he came over to Princeton to study under Church to get his PhD at Princeton, and they collaborated in a lot of the foundational concepts of computer science. And one of the things that's important to note here is that the Church-Turing thesis essentially means that the Church's lambda calculus and Turing's machines are essentially describing the same thing, that this universal computation concept that Turing was able to show for his machines also applied to this lambda calculus. And one way that you can think of this is that Turing's machines are kind of like the simplest computer that you could build, and that Church's lambda calculus is the simplest programming language you could describe. So now let's jump in here to the lambda calculus itself. So we're going to start off with kind of the syntax, and we're going to start easy, and then we're going to get farther into the semantics and such. But for the syntax, first of all, originally the lambda calculus was just using the 26 English lowercase letters, just one letter at a time. Over time, now we tend to put numbers on the end of them sometimes if we're running out of letters. We'll get to that in a minute on the alphabet version. The main kind of thing people recognize with the lambda calculus are these lambda functions. So a lambda function, you have a lambda symbol followed by a variable name, one variable name, and then a dot, and then something, just whatever it is, the function body at that point. It's kind of an opaque blob as far as you're concerned at that point in time. So that function body might just be a variable name, just the same variable name or a different variable name, or it could be another lambda function, so it could be beginning another lambda something, or it could be something in parentheses, or it could be some stuff with spaces in between. There's all kinds of things that it could be. But that is what's inside of the body. So let's look at some examples. So you can have a really simple lambda function, which is just this lambda x dot x. That's what we would call the identity function. You just we'll describe why here in a minute, but that's a really simple lambda function. Another one would be this lambda x dot lambda y dot x. See that the y doesn't even show up inside the function body, but it doesn't have to. It's just a lambda function with the variable x, and then blah blah blah. We don't know what the rest of that stuff is, and it just happens in this case that it's another lambda function, this lambda y dot x.
Just like with the lambda function, take the first.
Mm-hmm. Yep. Yeah, in a sense that you can think of that as practically being a function with two arguments where you just take the first. But it's worth remembering that in lambda calculus, literally, all functions only take one argument. And so what's actually happening here is it is a function that, given one argument, returns a different function that, given another argument, happens to return the same value that you gave it in the first time. So each of these things is only going it's going to be a function that takes one variable. So all functions take a variable.
Can I get the correct example for addition?
Oh, well, okay, I mean, yeah, we're gonna get there, yeah. You may recognize the next one then. So, another lambda function, lambda n dot lambda f dot lambda x dot f space n space f space x. We're going to cover that one here in a couple of slides. And of course, one of the most famous lambda functions is this last one, lambda f dot, and then lambda x dot f xx space, lambda x dot f space, and then xx again. So it's like, that's a strange looking pattern. So, those are just lambda functions. We'll get to what they mean later. Those are just lambda functions. So now function application. So to indicate that a function, you know, should be applied to a particular expression. So now you're wanting to like execute a function. We're just talking about syntax. We're not actually doing it yet. We're just saying how you would say that's what's going to happen. You just put the function name and then space something else. And since we know that all lambda functions take exactly one variable, that none of them take 0, none of them take 2, they all take 1. That means that whenever you have something space something else, that means that the first thing is the function, the second thing is the thing that's going to be passed into the function. That's it. That's the whole language. So it doesn't matter what the value is. Maybe it's another function. Maybe it's just a variable. Maybe it's parentheses and a whole bunch of spaces and a bunch of stuff inside of there, or 12 layers deep. Doesn't matter. Whatever it is, blah, it's going to get potentially, once we get to that spot.
We can clarify, even if it is a variable, it's effectively just a container for a function.
Yeah. As we said, it's only functions all the way down, but we'll see what that means here in a minute. So application of a function variable, it's worth remembering when we said that there's, you're talking about something space something else. That's function application, and it doesn't matter what's in the right-hand side, the variable that's getting passed in. But it's also worth pointing out on the left-hand side, that could be a variable. Like, it could be that the function you're going to execute you don't know yet. That's another thing that some other programming languages that came later didn't have, even though lambda calculus was like one of the first ones. The idea that you could swap out which function is going to operate on this thing is something baked in from the beginning. So in this particular case, you don't know what the f is up front. And you also don't know what the n is. That's also worth noting. Here we have n space f space x. Seems to imply that running in with f is going to give us back some function, which presumably is going to take another thing, x. So, kind of interesting.
Make sure, we go over like the order in which this is applying. Like, how to read this.
We can,
Unless it's coming later.
no, I mean, go for it. I mean,
so I'm reading it right, it's like, I apply n to f, that gives me a function, I apply that to x, and I'm applying that first f to the result of all of that.
that's correct, that's correct, yeah. That aspect is, there's no ambiguity on that aspect, yeah. So did you catch that? That means what this is effectively eventually going to be. Like if we were talking about executing it a piece at a time, then that means that f is going to get passed into n. The result of that is going to be a function that we pass in x2, and the result of all of that, we're going to pass into f.
So that means it's kind of a recursive definition?
In a sense, yeah, a very specific recursive definition, yeah.
Okay.
Maybe a
I'll give it the
successive,
definition of recursive.
maybe a successive recursive definition.
But bottom line, just, everyone gets the order in which this is being applied.
Yeah. I thought you were saying it, the order of evaluation, and it's like, that is an interesting, the Church-Rosser theorem says that it does not matter. So.
Yeah, actually wasn't a distinction in there, I was just thinking about how we think of it in terms of, first this function applies to the thing next to it.
Yeah, yes, that's right, that's correct.
And you indicate parentheses to indicate you're applying one function to all of that.
Yeah, when we're talking about how how you can conceptualize the flow of data, yes, that is absolutely.
And then it's a matter of like order of operations. In the absence of any parentheses, it's the first one applies to the second.
Yes.
That applies to the next. That applies.
Yeah.
As opposed to starting from the.
Yep. So now we're getting into the semantics. So all of that was the syntax. So in a sense, everything from lambda calculus, you could describe a regular expression that would say whether what you gave me was the correct lambda function or lambda calculus expression, just based off of those things. So that's the thing to keep in mind in the future as we talk about some of these different concepts about programming languages. Syntax are the things that you could theoretically get from some kind of a fancy regular expression. Semantics are the things that, what does that mean when you try to use this programming language? So now we're getting into semantics. So there are 4 different notions of these conversions. We're going to go through them a piece at a time. I actually have most documentation on alpha conversion, which is funny because that's the one that will be the least trouble for everyone in here. But alpha conversion just means it doesn't matter what the name of the variable is. It just has to match. That's all that matters. You see, when lambda calculus first came out, this whole programming thing was still really new, and this idea of like variable scope was not a thing that people had ever thought of before, and so they had to spend a whole lot of time explaining that like, no, it's okay, you can just replace the names of the variables later on, it's okay. And so we have this special operation, this arrow sub alpha, that is the lambda, it is the alpha conversion on a lambda expression. And so here's an example. You have something called lambda x dot lambda x dot x. And so what we would say is on the outside, this lambda x is a bound variable. But then inside of the body of that lambda x, so remember, we don't care what's on the inside of it. So what's inside of that thing is a different bound variable, which just also happens to be called x. It's a different variable. But now inside of the body of that function, we're talking about x. Well, that inside x doesn't necessarily have anything at all to do with the outside one. It's totally unrelated. And to make that easier to see, we have this alpha conversion thing where we're just like, okay, we're just going to replace the letter. So in this case, we've just swapped out the inside variable x with the letter y.
So
Doesn't change anything.
So stupid question, alpha conversion is just don't have confusing variable names.
Well, as we'll see, like you're gonna get very confusing variable names because especially when you start dealing with like true and falses, and you might have true nested like a bunch of times. Well, your definitions still have the same thing, and so if you were worried about confusing yourself, these days the computers will take care of it for you. But back then, it was a really big concern, and so you needed to be able to change the variable. And so we, in this case, changed x to a y. It doesn't actually change the meaning of that statement at all. Alpha conversion does not change the meaning of a lambda expression. It just changes the variable name so that you're not confusing yourself. That's it. So nothing special. Yeah. And so yeah, like we said, that it was still kind of new. People were really stressed. Oh my God, the number of papers about like, if you're starting with X, then you should go to Y and Z, but you should never start with X if you think you're going to have more than 3 layers of indentation. That's when you should start with A. And it's like, oh my God.
Did they really discuss that?
Yeah, they were really freaking worried about this crap in the early days. Like,
It would have been so easy to get a PhD back then.
yeah, I don't think you get a PhD from it, but you got published in some journal or something. Like, there were people who were really worried about this stuff at one point in time, and it is like, it's funny that so much stress was made about this. When
But
today,
they were probably made fun of as well. I mean, like, a lot of people worry about like, silly stuff today as well, right?
For sure.
And, like,
in fairness, there was a war on, so like I can understand like why they were like maybe preoccupied. But like today we have a much simpler thing. If you ever deal with like automated debugging systems, you're going to see the pattern that we have, which is, yeah, we just leave the variable name the same. We just slap a number on the end. Which, if you ever deal with like GDB or deal with any of like a interactive theorem prover or something like that, when it's doing these kinds of alpha conversions under the hood, this is what it's doing. Is it just keeps the variable name the same and slaps a number at the end. Like, not a confusing thing to programmers these days, but yeah.
Since you were talking about the early days, when did the like switchover happen from like primitive recursive functions and recursive functions to like lambda calculus? Because my understanding was that Church originally was doing with like, the minimization or like the unbounded search operator and stuff like that, and then eventually switched over to lambda calculus, but I never figured out when that happened or how.
So I think so. so the general recursion stuff was still going on, and it was still like hot when all this was happening.
Okay.
It was hard to wrap the head around what exactly was going on with Gödel stuff, and that's why Church was specifically going to lambda calculus for that problem, for the Scheidung's problem. That was part of it. Like, he was trying to solve a variety of problems in that space, and he was trying to get the lambda calculus to be precise enough about what it was that he was talking about. And because that was the same thing that Turing was dealing with. It wasn't so much about trying to describe, like, their goal was not to describe some new thing. It was trying to get the level of precision needed to speak clearly about a subtle, complex topic. And that was why they went to lambda calculus.
Okay.
So
But
his
like
students,
from the like recursive functions, like that has, that's kind of the same, but like, it doesn't have the sort of, it feels like hacky and like not generic, right?
Yeah.
It's like, but that was not actually the motivation, or like.
well, so he was working with a lot. I mean, like, Claney was one of his students who also worked in this area. All of those people were working together in the realm of general recursion, but specifically the lambda calculus and the Turing machine were like, they had the goal of trying to figure out things like the Scheidung's problem.
Okay.
That was the goal. And so it maybe not just only that, like, I think they wanted to build the kind of tool that could help them speak clearly about very subtle logical points like that without being afraid that they did something wrong. And that was why both of them tried to build these like really mechanized systems for talking about these things, as opposed to general recursion, which is a very powerful tool, but it's so powerful and it has so many slightly different meanings for different people that was part of the problem. Is like, it was trying to remove the communication barriers here.
Okay.
So, yeah, as you can see, the previous example, where we're doing our alpha conversion, lambda x dot x, lambda x dot x, now we would just convert the inner one to lambda, x1 instead of just lambda x. So, probably not a big surprise. Here is the big one, beta reduction. This is the heart of lambda calculus. This is the thing that makes lambda calculus like a model of computation, even though it's really simple. All it is doing is actually doing the application we were describing earlier. That's it. That's all it does. So you take a lambda function followed by an argument, and it basically eats that lambda variable name dot off the front, replaces it with the body of that function, just replacing every copy of that variable on the inside with whatever the heck it was you had on the outside. Still doesn't matter if it was like another lambda function, it could be like a variable name, it could be some really complicated thing with some parentheses and some spaces and really nested 12 layers deep, doesn't matter. Like, it's just gonna replace it, however many times it shows up. That's it. That is all that beta reduction does. So here's some examples of it. So if you had the identity function that we showed earlier, lambda x dot x, and so we put parentheses around there to make it clear that's the lambda function we're talking about, and then space a, that beta reduces to a. Okay? And then here's a more complicated one. You may recognize it because you've already mentioned it, but we're gonna just treat it as if it's we have no idea what it means. It's just some lambda. It's just a bunch of lambda things. We don't have to know what it means. It's just a bunch of lambda things. We don't have to know what this means. We can perform the operation. So in this case, we have 3 different lambda functions, all spaces in between them. So we know, okay, beta reduction. That means we take the first 2 and substitute the second one in for the variable on the first one. That's it. So in this case, we beta reduce this to, we chop that lambda x dot off the front of the first one, and substitute in this lambda a, lambda b dot a, in for the x.
Only do it to the x.
Only to the x. We don't do anything to the y. And so this results in a function, a new function, this lambda y, which now has as its interior just the value that happened to have been the second one. And then we didn't do anything with the third function there, because beta reduction only takes one variable, puts it into a function, that's it. We left alone that last one. But of course, now we can further beta reduce that thing that we just spit out here. So we did that. And you can see, well, it's kind of interesting. This y, you'll notice, didn't show up anywhere inside of the body. So it just means that we threw it away. And so that gives us this, you know, lambda a dot lambda b dot a. And if you're curious, that is my type theory for all hat is beta reduction. So, cool.
That specific equation?
No, well, it's just a more generalized version. So this syntax is a little bit different. I guess we can pass it around. The syntax is a little bit different. It's just showing that it's replacing the every copy of u inside of t with x. Every copy of t x with u. Sorry. So yeah. So feel free to grab the pizza.
Yeah,
Can I
I'm
translate
just
that
trying to
real
make
quick?
sure I pick a spot close enough so we can see.
Oh yeah.
So we were looking at the hat, he has like the reduction and like.
Yeah, the beta reduction. Yeah.
See, there's a roundabout way, that's applying the truth function. That's just
Yeah,
the
yeah,
first option.
you got
That's
it.
really
Yeah.
roundabout way of doing it. I think everybody catch that.
Yeah.
It's a lot of variables.
Well, they haven't seen true yet. I said we've just left it as a, we don't know what this is. So that's beta
Didn't
reduction.
mean to solve the whole thing.
Beta is the important one. That's the one that makes everything happen. That's the meat of lambda calculus. So now we have this other thing called eta reduction. And actually eta reduction we've already seen. That was the last thing on the previous slide. So when you know that a variable doesn't actually show up anywhere in the body, you can just throw out the variable up front. And that is called beta reduction. So sometimes if you're doing processing of a lambda calculus expression, you don't beta reduction is not only the important thing, but it is also the thing that can be expensive, the thing where things can go wrong. Beta reduction's the kind of one of the easier cases of that. If you ever happen to look through and you see like, oh, there's a variable which never actually shows up in the body, we can just throw that variable away. It's okay. We can just move on. And that has a special name, which is beta reduction. Then the last one, delta conversion. Delta conversion. This one does not have a consistent name from different people. So that's, if you see people talking about delta conversion, you got to be aware they could be talking about different things. So there are some people for which delta conversion means that there's a predefined list of things which are just like optimizations. So there's like a really common pattern that you'll see. You know, maybe you'll have like a particular arithmetic operation, and we know it would save us a lot of time in beta reduction if we just replace the whole thing right off the bat. That is one idea. There's another one where you have that every time you perform some kind of a lambda evaluation, a beta expression evaluation, then you cache that value somehow, and that delta conversion refers to the process of looking it up every single time. There's also people who are talking about something where it's like the full evaluation. That's what we might call big step semantics. There's people who delta conversion means a straight up big step semantics, which is weird. For this website we're going to look at in a minute, they're doing like the lightest weight version of it, which is just like, I'm going to give you a high level definition of something that's like gives you a fancy looking name, like the word true, or as you've discovered, a symbol that's not the word true, which is annoying. Here's a special symbol or a special word, which isn't a lambda calculus thing at all, but I'm gonna say that it means the same thing as a very specific lambda calculus thing. And I can swap back and forth using delta conversion. That is a definition I like better than these other ones, so that's the one I'm going with. And it's the one that this website uses, so.
So it's just binding expressions to what are effectively labels.
Yeah, it's a labels, basically.
I was gonna say variables, but no, confusing.
Yeah. So now, yeah.
It kind of sounds like p-graphs, equivalency graphs.
Yeah. So now we get into some weird stuff. Remember how I said it's all functions. We're all functions down here.
Yep.
There is no data except functions. Even true and false are functions with arbitrary, left, unspecified, like arguments.
But what about the arguments to the functions? Are they still functions as well?
Mm-hmm.
Yeah, they contain.
Yes,
those are the thing I was
it's
talking
functions
before.
all the way down. It's only functions. Now, it's functions of special shapes, and so sometimes that means that we don't have to keep evaluating them. Maybe what comes out at the end is a function. So for example, notice how there are no spaces here. So that means if you gave this to beta reduction is not going to do anything to just a true standing by itself, or just a false standing by itself. That would be the end of it. If it came up with just true, and that's it, that would be done. That would be the answer, whatever it is you're looking for. Or false, same thing. But if it was true followed by something, well, now true becomes a function, and it's going to do something. So, yeah. So it's kind of strange. So that means that now we have function definitions for and or and not. See, I'm using his magic delta conversion notion for that not there, because I didn't feel like writing, false and true down. But just know that it's not actually the word false and true, it's actually the whole lambda, expressions in there again. And so it's like, well, this seems weird, like, true is just a function that takes two things and it returns the first value, and false is take two things and return the second value. Like, that seems arbitrary, and it kind of is arbitrary, as it turns out. Like, it doesn't really matter. It's just that all of them have to match. That's the only thing about it. They just have to match each other. That is what is kind of special about this. And so it seems kind of interesting that, okay, it doesn't matter the order that these things are, as long as the ands and the ors and the nots and the trues and the falses and stuff match each other. It's this like relative notion of truth, which is kind of interesting. I don't know if you're familiar at all with constructive logic. It seems kind of like that, and like maybe there's a reason, and we'll get to that later. So now we get church numerals. So in the same way that like true and false are these weird function things, numbers are these weird function things too. So you get 0, which is lambda f dot lambda x dot x, and 1 is somehow lambda f dot lambda x f space x, and then 2 is f space fx. And you might notice that 0 is just an alpha conversion away from false. So 0 and false are the same thing in lambda calculus, according to alpha conversion.
Finally, I forgive them for using the same thing for them to see, right?
Yeah. So kind of interesting. You may have noticed a pattern there in the 1 and the 2. Maybe I could have gone farther, but this successor function, you can build all integers this way. So what ends up happening is you take any number, you can find what the successor of that number will be, and you're just building up. You go back here, it's just going to be another f on the front inside of the body of that function. So it's still gonna be lambda f dot lambda x dot, and then some number of f's before parenthesized, you know, copies of x. And it's the same thing here. That's what this function will build.
Or here, the successor thing is, like n plus the input, or the input plus n. It's kind of confusing, because from like, whatever, piano math and the lean proof assistant from a few months ago, the successor function is add one exactly, not add n, so, minor wires here.
Oh, no.
No?
Remember, functional programming, everything's a function. So, in this case, successor to 1. Did 1 is this function. So if you pass that in to successor, that's going to get passed in for when you evaluate it. It's going to get passed in as the value in. So that's going to be lambda f dot lambda x.
Or
f.
the successor takes any number as an input.
Yeah, the argument is a number. So the argument to successor is a number.
So I mean, it's compared contrasted with like the lean proof, so the successor is specifically add one exactly.
Well, that's what's happening here.
Is that,
No, it's in is the thing being added to. This f on the outside is the adding one here.
Okay, never mind.
Yeah. No, I mean, I absolutely see where you're coming from on this, but yeah, in this case, this f here is the one being added on. So this in fx is the definition of whatever the number was beforehand. So like your 2, 3, or something like that. Yeah, and this is where the slides started the not complete yet. Like I said, the rest of these slides are more for the people who aren't here rather than the people who are here, because now we are going to begin. Basically, we were showing multiplication and addition here, but that doesn't matter because we're going to jump straight over here to lambdacalc.dev. So if you want to play along, otherwise we'll do it together here. Okay. Let me know when you got it.
Just a second.
Yeah, you good? And I endorse this website because it makes it a lot less painful than trying to figure this out on your own. So let's do, and there's help if you want to follow along, because they have like a reasonable tutorial through some of this stuff if you want.
So wait, you just selected and highlighted and want to use the T's you're on the
Yeah, like copy paste is what I'm doing. But so we'll do the example they give right here, which is the identity function if you recognize it. The special syntax thing that's worth noting, because the backslash is only useful for creating a lambda inside of this context. Backslash just automatically creates a lambda for you. So, hooray JavaScript. So lambda x dot x, and then space a, press enter, and so now you see that it has parsed out. It's like, hey, I know what that is. That is a lambda expression that you're trying to do application on. So we click the next step, and it says this is basically implying by beta reduction. So because of beta, we have A, and that's it. You can't reduce this anymore. You click next step as many times as you want, and it won't do shit. Because it's already fully reduced. There's nothing we can do. So that's cool. There's other things we could do. Let's come on, where's my mouse? So let's see what is true or false. So unfortunately, their documentation seems to imply that you could just write or true false and that would work, but no. You have to copy these symbols, which is annoying. False. or true false. And now we can explore to see when we try to evaluate this lambda expression, what does it mean? So we click next step. And so this is saying by delta conversion, it converted the or symbol. So if you go over here on the left hand, or if you're using the mobile, it's at the top just collapsed or whatever. You can see that the or symbol has this special definition, lambda p dot lambda q dot p p q. And so it just expanded the or. That's all it did. Didn't do anything else. And so that's the nice thing about this way that they're doing it, instead of by using the version of delta conversion that they're doing, we can leave the true and the false alone for now. Like instead of having more lambda, we're like, okay, we've got it. Lambda, you know, the true thing is getting passed in as an argument. Cool, we can move on. So, okay, let's go evaluate, because we see it's a lambda function. Starts with a lambda with a variable. It's got crap in here that we don't care about. It happens to be lambda q dot ppq, but it does not matter. All we know is that something starts with lambda, and we have something with the function that comes after it, so we can apply it. So we do. So we swap in every copy of p for that value true. So in this case now it is lambda q dot true space q. Whatever the hell that means. Okay, cool. But now that means it's a lambda function, and we have one argument here at the end. Okay, another thing we can do a beta reduction on. So let's do another beta reduction. So what's going to happen next? Anybody?
Beta reduction of the false thing, or plug the false in for Q. Beta reduction.
Okay. So what's the, yeah, that's what it's going to do. So what is the output going to be at this point? Once we run this command, what do you think?
True, false.
Yep, it's just going to be true, false. Because all it's going to do is get rid of that lambda q in the front and then replace the q that's inside of there. We click next. True, false. It's like, cool. Well, that doesn't feel like an answer to true or false code. So,
You gotta unbox it with the
so now exactly. So now when we click next step, because we don't have any lambda things already exploded here, that means, okay, well then we have to do a delta expansion of some kind. And so we're going to do a delta expansion of the first thing, which is going to be this true. Okay, so now we've just exploded the definition of true. Is this?
Oh, we did that because you clicked on it?
Yeah, we clicked on the next step. You can also click on the symbols if you want to.
Oh, okay.
That will also work. If you want to explore what does it look like going through a different path, which again feels like it might be different in important ways, but it turns out that it's not because of the church roster theorem. But
It terminates.
well, it's not going to change whether it terminates. So church roster won't change whether it doesn't change the syntax. I don't think.
But
I think it makes
depending
it
on which
equally-
order you evaluate, it can non-terminate even if it would terminate otherwise. If you have an infinite loop and you ignore it outside of that,
So you can evaluating the wrong one can lead to.
it leads to non-termination for something that otherwise is well-defined.
Really? Okay.
That's why, like, at least my understanding was that I was like, why Haskell does lazy evaluation too. If you do the lazy like outside order versus like inside order.
Okay. I didn't. Okay. I believe that you're probably right. I didn't know that. I thought it didn't matter.
Yeah,
inside
if
of the
it
lambda.
terminates, they'll converge to the same thing, just in potentially different number of steps. But if they don't terminate, they can one of them can go off forever, one of them can finish.
Oh, interesting. Okay. Okay. Interesting. Okay. Thanks. Yeah. So expanding that first one, we get our weird definition of the word of the true. So now, because it's a lambda thing and we've got an argument being passed in, that means like, okay, well we can go and replace this x. So now it will be, anybody got it? What will come out of this when we click the next step?
Oh, is it gonna do beta reduction of
Yeah, it's gonna do a beta reduction because it's got a lambda there and it's got a thing being passed in.
Lambda y.
You're replacing the y with the
Yeah.
x?
So in this case, it's gonna replace the x, so it's gonna be, you're right, it's lambda y dot true, and then it's gonna be space false. So lambda y dot true space false. Okay? So now what is it gonna do? I think this thing is gonna say it's beta reduction, but that will give you a hint that I would call it a different thing that it's about to do.
Yeah, I think you could just a single variable function, beta reduction, and plug in, or no, just throw out the input. Just throw out the false at the end.
Yes.
Because it's not.
As I had mentioned earlier, we might even call that beta reduction.
Yes.
Because it means that the variable y doesn't even, I mean, like, it shows up inside of true, but like not really because of alpha conversion. It's not the same y, it's a different y, you know? So, I think it's gonna say beta, but I would call it beta reduction, so yeah. Just chopped off that thing, now it's just true. And we can next step this one more time, that'll do a delta conversion, but now that thing can't be beta reduced, so we're done. And so, okay, now if we go back up, what were we doing? Or true, false, that's true. Hey, that looks like the right answer. So, on the right side, we can kind of identify what does true and false look like. So I'm going to use a definition here. Plus 1, 2, 3. Okay. So we're going to see is 1 plus 2 equal to 3. We would expect that to be true.
It's fine with EQ.
Well, I think it's just the
Browser.
browser. It's not the
Browser.
yeah. See, it recognized it. So up front, it's gonna do a delta conversion. It sees the EQ there. It's gonna be like, okay, I know what to do with that. It's gonna expand that into a lambda expression. And you see, well, hey, wait a second. This looks like it's complicated. It's like, no. Remember, this is in parentheses. So the whole thing in parentheses, that plus 1, 2, that whole thing is gonna be passed in as the argument to this lambda function. In this case, it's gonna replace the lambda in. So what will come out on the other side is gonna be lambda in dot
And then all the
and then less than or equal to plus 1, 2 in, and then less than or equal to, you know, in plus 1, 2. So we do that next step. Cool. And like, hey, wait a second, this whole thing is now an apply because it's a lambda expression. And remember, we had this 3 sitting here off on the end, all by its lonely. Now we can pull that in as the argument. So 3 is going to get swapped in here for the end. So as soon as we do that, boom. Now we're back to no lambda expressions, but a bunch of parentheses. So we can do another delta expansion. It's going to do it on the first thing on the left, just because that's the way this interpreter is set up to do it. So it's expanding the definition of and. This lambda p dot lambda q dot pqp. And so it's going to take the first blob inside of parentheses, which in this case is a less than or equal to plus 1, 2, 3.
And from the student perspective, that thing after it is like the second argument, but we don't have multi-argument functions.
Exactly. Yeah. So this other thing is like the second, but we don't have any kind of a second argument.
We're all current.
That's right. So let's go ahead to the next step. So we did a beta reduction on the P. So that puts, you know, it's gonna get big pretty quick. You got this lambda Q, and then you got this whole thing in parentheses, and then Q, the whole thing in parentheses, because the original was PQP. But like, hey, wait a second. You know, now it's a lambda Q thing with some other crap in parentheses afterwards. We can do beta reduction on that. So we do, and boom, now it's a new thing with just parentheses and evaluation and And, you know, so now delta, conversion on that less than or equal to, cool. So unboxes that. Okay, now we're getting to the first kind of interesting one. We got this is 0. So we're just checking to see, is 1 plus 2 minus 3 0? So kind of interesting, okay.
First unboxes that.
It's going to unbox the as 0, so that is 0 has a special definition here. Okay, and you see we've got multiple layers of things that are going to be evaluated later, but for now we've got a thing in parentheses that we can apply to that lambda n. So we're going to do that. So that's weird. We got a minus here in front, but okay. It's a thing that we can evaluate. So we'll do a delta expansion on minus, whatever that is going to give us. Is delta n dot n predecessor m. Okay? And we're doing it on this first 1 plus 2. Okay? Cool.
First did a big reduction on the
Yeah, and now we gotta pull in that 3 because we got that second variable here, that n. Okay. So now here's where it starts to get interesting. It starts to look a little bit different than you might have expected as a programming language.
Plus 3.
We're going to run the function called 3 on predecessor plus 1, 2. Like what? So here's the definition of the function called 3, which is lambda f dot lambda x dot ffx. The same number of f's as there are numbers above 0. That thing is. Okay, and we're going to run that on the predecessor function.
So plug pred into F.
It's just going to plug pred into f. So this is going to look real weird. Lambda x dot pred x on to plus 1, 2. Alright, so that means, hey, we got another lambda function. We got a lambda x in the front. We got a thing that we can plug in. So, okay, we're going to.
So it already just did, that's what already applied that and got that to 17. The thing about.
No, this is the 17th step. That's where we're at.
Oh, gotcha, it's after, but it's still after applying that.
17 is centered, it's centered vertically in that whole
Yeah.
block.
Yeah. So.
Wait, I still lost you. That green blob, it's doing another reduction on that green blob.
Yeah, it's going to do a reduction on this green block. This is the first thing.
Wait, oh, all of this is 17.
Yeah.
17.
This is the 17th step.
I know, but it's not 17, it's not segmented.
No, yeah.
Parts it looked like
Yeah.
17 was
This
segmented.
whole thing is one big expression. We're just
I'm
putting on
misreading,
new
I'm
lines.
misreading.
Yeah,
Gotcha.
we're just putting on new lines because of the
Gotcha.
spaces.
I should have put the 17 at the top.
Yeah, I think that would also make sense. So we did the beta reduction. So now we got pred plus 1, 2, bunch of stuff.
It applied, it substituted in.
Yeah, substituted in plus 1, 2 for
Every
the
x.
x, which is at the end of this pred. So we're going to do that. So now pred.
Stuff reduced.
Now predecessor is a large beast, as we see. And then we're applying this on pred plus 1, 2. So that means the whole thing is going to get passed in for n. Which, if you notice, there's only one copy of n. It's at the very beginning. So kind of interesting. This whole thing is only going. Let's do next. Oh boy. Now the formatter's having a hard time with this now. Like, so it's lambda f, lambda x, pred plus 1, 2, all this stuff. But if you notice, if you scroll back up, you're like, wait, where the hell did this lambda x dot false come from? So it
It
came.
was in there as a step.
Yeah, it came from there, and so then where did that come from? That came from there. Came from there. Like somewhere we got this lambda x false thing showing up. Trace it back. Came out of here. Lambda x false from step 11. It's like, what was that? That was the result of the is 0. So that's one of the weird ways that this lambda calculus stuff works is you may set up an argument to be passed to a later function way earlier on, and then you won't even get there until far down. That's why they call this sometimes beta hell. To try to figure out where the hell did this shit come from? Like
Also for some other.
Wait, so why would you do it for fun then?
what?
Why would you do it for fun then?
I mean, why do
We're
people
not
program
making-
for fun?
We're
You know?
making computers do it. Computers are
Yeah.
breaking through all this stuff. We're not doing this by hand.
Yeah, and then, like, if you wanted to do this on a daily basis, you would not be doing this by hand. We're doing this right now just to see how it works, to play around with it. But like, yes, you wouldn't do this by hand, like, ever.
On a related
Not
topic
these
of
days, yeah.
computers. This whole problem of working the problem this way through lambda calculus, is this any less or more complicated than doing it on like a Turing machine? Like if we're comparing fundamental models of computation, is it?
It's essentially the same thing. Depending on what you're trying to do, it may be faster
Well,
or.
like, I meant for like in this example, like the whole concept of deciding if 1 plus 2 is equal to 3 equals 0 problem.
Yeah, it would just be depending on how you modeled it. And another aspect of this is a lot of, even in a real computer or whatever, the lambda calculus is not going to go one step at a time with beta. And it's also, you're not going to use lambda calculus for doing real world stuff either. Like, you would use, even if you're using a functional language, they're not
It converts
they're
it to
not functions
efficient-
all the way down.
It converts it to efficient assembly.
Yeah, yeah.
Or some interpreter or something.
Yeah. And so we can keep going, so you see.
Just a question on that, so would you use this to prove that your program compiles correctly? Like, you do an equivalency from C code, assembly code to this, and then run through the reductions and prove that this is correct, but not performant, but then project it back to assembly that is follows exactly what Lambda proved.
Probably not in the untyped lambda. So this is the untyped lambda calculus is what we're playing with, and this is Turing complete. But we'll get to that in a minute.
Alright.
So potentially, but probably not in the untyped lambda calculus. So if you keep, we can keep going. We'll skip 100 steps. You can go play with this if we're running a little low on time now. We'll skip 100 steps.
Oh, this is still like 100 steps? Okay.
This is another 100 steps later.
Oh, damn.
And finally, at step 118, we come to the answer that 1 plus 2 equals 3.
Wait, so that's only like for a 3 preposition or whatever statement of the at the beginning, right?
Mhm. Yeah, it's 118 steps. Now again, these are 118 very, very simple steps. So it is not going to take your computer very long to perform this if you were actually telling it to go, even on the lambda calculus. And in practice, you would not actually use the lambda calculus if you wanted to do something really important. So now, kind of interesting, we eventually came up with the right answer. Now let's look at what happens if you did not pay attention to the part inside of the documentation that says that this is prefix notation, and you just did this shit. 1 plus 2 equals 3.
But you didn't do the space after plus. Do you need to do the space after plus?
No, I don't think it matters that much. Okay, hold it. 1 plus 2 equals 3. Go. Okay? Let's just skip 100 steps on this one. Okay.
Is it going to go forever or
No, it will terminate.
Just
This
one?
one will terminate.
after how many steps?
I can't remember.
It's not getting shorter.
Couple hundred for sure. Come on, where's my mouse? There we go. Maybe it's like 186 or something. I'm trying to remember. I did a couple different examples, and one of them was like 186, but.
So like that, whatever the Principia Mathematica, whatever, 100-page proof of 1 + 1 = 2 or something.
Yeah, yeah.
Is there a way to just scroll to the end?
Probably, honestly.
And it's capital G.
Another 100 steps.
Oh, G.
Wait, so what step is that? What is the last step here?
That would have been like 2 or 1 or 2 or 2 or something.
But, oh wait, you made it that much harder
That was
by
201.
using the index notation? What's
Five.
different about inputting it this way? It was the same.
It's not practically valid.
Oh, and it had to do its own.
But it's lambda calculus, so it's gonna try it anyways.
Wait, so what was the
Oh.
answer?
Like, so you gave it something knowingly invalid? Oh.
But it's lambda calculus. It's the untyped lambda calculus.
So
So
what
it'll
was-
do it.
What
It'll
was
just
the,
go run.
what was the answer? Did it have, it didn't
Oh.
have the correct answer because it wasn't valid, right?
Hold on.
Yeah, there we go.
Let's go get the answer. We can still go. Another 100 steps. This terminates. I know this one terminates.
Why did it stop at 201? How was that?
So that was 301, because I told it 100 steps. It labels the first step 1, and then it did 100 steps, and so it's 101, and
It's
201.
100 plus 100 plus 1.
301. Yeah.
And that's what it is, lambda calculus.
It's just the how this thing.
Wait, so they're doing like the lambda thing and they do like an O plus 1? Like, what the fuck is that? Why is it the plus 1?
But
No,
first
it's
one is
the
called-
first one is 1. It's not it's step 0. It's step.
Oh.
It's a one-off.
So hold on, to go back, so you said
Why
like by
do they-
putting the EQ in the wrong place is invalid. It doesn't really have a concept of invalid.
Yeah,
It's still valid
that's
in
true.
some
It's still valid in some sense. Yeah, it's a thing.
That was actually the other thing that came up to me as interesting, when you find the concept of like addition,
Yeah.
or even and more, it's like, we think of them as adding integers, but you can put any function into them. Simply by defining addition, you define something that's general enough that doesn't just apply to integers or, relate with these integers.
Yeah, yeah.
Mind blowing.
But isn't it like the if you don't put any sign or any operator, you can just assume that it's a plus also, right?
You can what? Submit.
You can just assume that it's a plus.
Yeah. You can
So
put
like
anything.
the-
Yeah.
Yeah, so the plus, like the 30 plus, or like the 1 plus 2,
Mhm.
you could handle it as like, plus 1 plus, 0 plus 2. So like, just like the regular plus, you could also handle it as a number, as a 0 number, right?
Mm-hmm.
Like the sign, like the sign in the middle, could be just like a regular number.
You could do any number of things. I mean, there's any all kinds of things that you could do. Oh, is it gonna crash? Come on, don't crash.
Is it running in the browser or is it running?
It's running in the browser. Yeah, they're not running this shit on the server.
You run it on your own computer.
Yeah. Okay, cool.
How much RAM do you have?
16 gigs. Come
Wait, is it
on.
ThinkPad? Why don't you have more than 16 gigs?
This is an X220.
Okay.
16 gigs was more than they would sell you back then.
I think I have like X230. It does have like 16 gigs.
Yeah. Come on, you can do it.
Did you have to do more than 1,000 steps almost?
More than 100?
Did you
Yeah.
put 100 or?
Yeah, just doing 100 at a time.
Aw. I mean, the result is like meaningless.
It's having a hard enough time with 100 at a time. Getting close on time. I just wanted to show you what it looks like. You can do it. Little engine that could. Come on. You can do it. You can do it.
Wait, did you try it on this computer or how did you try it at home?
It was on this computer, but I didn't run as other things in the background.
Is it like swapping like crazy now or what is going on?
No, I think it's just Chrome being a shit.
So why are you using Chrome then?
Well, that's a fair question, but I've also got Firefox, but
So you tell us you have VI and Emacs.
well, I have them both installed.
Yeah.
Yeah, you are tricky. You have to not have Firefox installed.
Like 500 something. I know a terminus. I did it the other day. It is deterministic when you're not like clicking around in it. All right. Well.
Does it go into cycles or does it keep just growing and growing? I can't.
Oh, there it is. It finished. All right. 531. Okay. Oh, is that gonna crash it?
Oh, wait, you finished?
Okay. So anyways, it finished, and it is a function that takes lambda x dot lambda x1, and then a bunch of shit starts to happen, and this is terminated. This is fully reduced. There is no more beta reduction that you can do on this. No more delta reduction. This is over. This crap is done. That's the end of it. That's the answer. This thing. And so this is what happens when you enter beta hell. When you did something wrong, you don't know why. You don't know where did all this shit come from? Who knows? And in this particular case, it was because we did an incorrect syntax. We did infix. We treated these prefix notation as if they were infix. And untyped lambda calculus is not going to stop you from doing that. So how do you fix that? Well, one of the things that we do is called the simply typed lambda calculus. That's one of the options. And what you would do is inside of your lambda functions, instead of it just being just the name of the variable, you would do the name of the variable, colon, and then some type. Now remember, it's lambda calculus, so everything's a function. So it just means something that has a particular shape with regard to inputs and outputs. That's all it is. There's nothing special going on. It's just something about the shape of inputs and outputs that is the only thing you've got for your types. So it's kind of interesting that that can kind of save you from this kind of thing. What's surprising is that by adding this simply typed lambda calculus, just adding these types in and making it so that, okay, you can't evaluate, like your beta reduction won't run unless it sees that the thing that you passed in is actually the thing that we're expecting it to be. And it's interesting because, when you do this simply typed lambda calculus, based off of the things that you passed in and the shape of the function inside, we can know a priori what is the data type that comes out. Because we know what functions got passed in, we know what you're doing with it inside of there, we can calculate what the data type of this function would be on the outside. So that's kind of cool. But that modification makes the simply typed lambda calculus not Turing complete. It's not Turing complete, which is kind of a surprise. But the untyped lambda calculus is Turing complete. You can get things which never halt. Like, we don't know for sure if I type something slightly different than that, maybe it never finishes, maybe it never halts. It's one of those things that defies the Scheiding's problem, as we were talking about earlier. But you can't get to one of those from the simply typed lambda calculus. Well, that's kind of interesting. But the other thing that's kind of interesting is this idea of this predictive type thing that we were talking about there. So when the types are just having to do with the shape of the functions that you're passing in, and then something about the shapes of the functions that get passed in as arguments gives you knowledge about what thing comes out the other side. And and it has to do with relative notions of truth and everything like that. Well, it turns out that is the exact same thing that we have with constructive logic, which is where you get the Curry-Howard isomorphism, the Curry-Howard correspondence. It turns out that the simply typed lambda calculus is the same conceptual structure as mathematical proofs in constructive logic. And that is the basis of several of the major interactive theorem provers like Ruck, Koch. Several of these systems are based off of this concept. And even ones that aren't based primarily off of this concept still are heavily influenced by that fact. The fact that this notion of constructive logic and the simply typed lambda calculus are essentially talking about the same thing. It gives us powerful ways of thinking about either one of them. So in a sense that the theorem that you're trying to prove in constructive logic is kind of like the type in the simply typed lambda calculus. And that the program that you're using to construct it is like the proof in constructive logic. They're the same thing. And that's where this idea that you may see sometimes where the programs are proofs, the programs equal proofs or things like that. That notion comes from this idea of the Curry-Howard correspondence, Curry-Howard isomorphism. Is that once you add the types to lambda calculus, it makes it no longer be Turing complete, but it does make it behave just like the mathematical proof system that people like to use these days, or at least computer scientists like to use these days. I think some mathematicians are not fans of it, but a lot of computer scientists prefer constructive logic.
Could you say it seems like without types you can express an infinite recursion, but with types you can't?
Infinite recursion? Yeah, I guess
Just
that
came
would
up
be,
with that, so I don't know if that's a legal term.
I guess that would be true. Yeah.
Now, it is to me it's not intuitive why adding types prevents infinite recursion. If types control the shape.
Yeah.
Suppose that's it.
I think you would be able to do like really simple recursion as long as the function was always returning the same thing. But if your function was doing anything, then that would be presumably some kind of a change in the type at that point in time. And so then you wouldn't be able to have something which would recurse infinitely like that. Like you wouldn't be able to, I mean that's where like the halting thing comes in. You couldn't describe a problem that would suddenly
Is the type
change.
become infinite as well? Or if you have an infinite recursion function returns itself, well, the type definition is also infinite.
Yeah. Well, it would be yes, unless the function itself never changed itself. You know, like if it was just if it was like an infinite loop that literally did nothing, then I don't see why that would be a problem because its type wouldn't be changing, and so then every single time it ran, it would be returning the same thing. And then that would you would be able to predict the type of that. But if you were doing something, I think, I mean, I don't know for sure, this is not my primary area, but I think that would be the case, but I don't think you would be able to do anything interesting with it. So yeah, that is where we are at on that stuff. Questions, thoughts? The goal is in a future talk, we'll get a little bit more into probably the type of lambda calculus and the Curry-Howard isomorphism itself, because that's important for a lot of things we might do to construct proofs about the behavior of a program. Is you would probably be using, you're not going to be writing it in lambda calculus, but under the hood, the logic or something is going to be related.
One of the things I would ask about things, but it didn't cover it, so aren't related. I remember doing it, they're trying to make sense of the whole like combinator concept and why that's
Yeah.
necessary and all that magic around it.
Yeah, so.
Just cause it's cool in terms of it, like, has a concept of like, whatever, self-reference and the whole, how that incorporates the Godinian paradox of whatever.
Yeah, so that was the last one, but we didn't mention what it was. This last function is the Y combinator. Which even though there's no Y's in it, but that's what that is. So it is lambda f dot lambda x dot f. So it's this lambda f xx on the other side, basically, inside of the outer lambda f. This lambda function is called the Y combinator. We usually write it with a capital Y, and it's kind of the basis of recursion in the untyped lambda calculus. If you want nice behaving recursion, you can use something like this.
Does it reduce to hacker news?
Yeah, we're gonna say the hacker
It's
news.
where the name.
Yeah, it's where the name comes from.
But yeah, I think the thing was gonna say, yeah, it's just neat that you can like have a function like refer to itself without naming the function, which is the other cool thing it does.
Yep, yep.
And in reading this, I also found out there are like other ways to accomplish that. There are other
Yeah,
combinators that.
there's
do
other
that.
combinators. Some of them also have notions of recursion. Some of them do other things that are interesting. So there's other like high level structural things which are interesting patterns that people have found about the lambda calculus. Yeah. Cool.
Just gotta get out of the room by what time?
Yeah, we'll have to get out here. We have to be cleaned and out before 9. So. Yeah, thanks for coming out.
Thank you.
So,
Thank you for hosting us.
let's see, so, next month, so for August, we'll still have plenty of time before I leave, because I won't leave until a couple days afterwards, but for September, it's gonna be tight on time. I'm going to Europe for an SEL4 conference in early September, so a couple of days after the conference, after the formal methods group. So for September, there's a possibility, Rob, you were suggesting that maybe doing like folks who give lightning talks or something that they play around with or something.
Yeah, I mean, the most I would contribute was a bunch of links and videos, which are in my tabs because I tend to look at them.
Yeah, that's fair.
But that's the thing. Depending on what time we have actually between here and there, I played around with like using some of the AIs to ask some questions about Isabel and Lean and stuff, but I'm not good enough to judge if it's useful. Or maybe I should say I'm at the point where anything they say is useful.
Yeah.
But yeah, we could do a round robin of that type of stuff. I think, another discussion that might be interesting is to ask people about books, online lectures, and other material, and say like, hey, like if we had a top 3 reading list to get started, like what would be on it? Kind of group source, some kind of list that might be useful.
Sounds cool.
Yeah, that sounds good. We can get a bunch of that. I've got a bunch of stuff I could share. I've been putting together a YouTube playlist kind of off and on, not very seriously for a while, but I've got several things on there that could be of interest.
I saw that there was an Austin Formal Methods like YouTube video, or is there like a
Yeah, it's
channel?
probably just the
Okay.
recordings that they do for this. So because they stream it, it's automatically recorded in YouTube.
Oh,
And so
really?
that's part of the Austin Tech Live channel.
Ah.
They do it live, so like you can literally like watch it like right now.
Oh, really?
Yeah,
Yeah.
yeah.
I think it's like delayed for like maybe like 30 seconds or whatever.
Yeah, it's a little bit of a delay, but not a lot.
They do it for like most of the meetups. So like Joshua Bayer.
It's just barely
like,
enough time for you to run down the hallway and yank the no, I'm kidding.
Yeah, right.
I just driving here as well.
Oh, wow.
Oh, really?
Yeah.
Let's see.
Yeah, Joshua Bayer, he got like all the names. So like it's called Austin Tech Live. So like none of them actually have, you know, like Capital Factory thing, but like it's all owned by Capital Factory, right?
Oh wow, yeah.
So the name is actually Austin Tech Live
Yeah.
I like it.
on YouTube.
Yeah. It's like ACL.
I think one of the confusing things is that like when you go in the app, it doesn't show under videos. So if you go in the app under videos, it doesn't show there.
Oh,
So you have to go to look at the videos of the recordings. You have to go into the live thing, and then you can see the old recordings under the live thing.
Yeah.
So
yeah.
like it's always confusing to me like when I use it like the first
But you
time
can-
after a while.
But you
know,
can
like,
share
after
a
I
link or
use it.
whatever though.
Huh?
You can share a link or whatever.
Yeah, you can share a link, but like just like when you find the Austin Tech Live, right? If you go into the videos, like all the videos are like 5 years old or whatever, right? I'm like,
Yeah.
where's all the recent stuff, right?
Wow,
Yeah.
yeah.
But then you click on the live thing and you find all of them.
Yep. We got more of the stickers if anybody needs some more.
I use one.
Yeah, yeah.
I need one more, cause I gotta,
Yeah, go for it.
I left out.
Take much more.
I have some of these across like 10 or 12 different coffee shops now.
Nice. Once again, if you guys need one of these parking codes, I strongly suggest you take one. Because man, is it expensive if you don't.
And then across the street. More parties than I expected.
So what if it would have like opened up and like split all over the room?
Yeah, that's alright.
We would have just stuck where they landed.
That's not you or HDMI.
What to do with it.
It is not the, I've got HDMI's in here, but that's.
Did you get your Pixel to work with the HDMI thing? Remember we were trying to do that?
Yeah, my older one did not ever work, but it was.
Wait, which one was the older one? 8?
No, I think it was like the 7 or something.
Oh, 7 doesn't support that.
That's what I'm saying, I don't think it did. This one does, cause I've used it before. I haven't
Why did
done-
you try it? Because I think like they edited it 8, so like 8 is the first one that supports it.
Well, so it's the first one that supports it in a while. They used to support it with the older ones. Like the 2 and the 3 or whatever did.
I don't think, I have 2, I don't think it supports it.
Some of the older ones definitely did, but you had to, there was something you had to do on the software side as well.
Is it for taking?
Thanks, Charlie.
I don't
Yeah,
want
thanks.
the,
Thanks for coming out.
Can I take this one
Thanks
without?
for coming out.
Charlie, assume you want us to take this away or?
Yeah, I can't eat any of that pizza right now.
Yeah, you said it's for the taking, so split it up.
Yeah. I'm wearing this because I had food poisoning on Monday, but like 99% sure it was food poisoning, which is why I'm wearing a mask. Like all of the symptoms say food poisoning. So.
You want to leave, these here to be consumed or next time or whatever?
Put it in the refrigerator. Yeah, do they want them in the refrigerator or something, or can you just leave them here?
Oh, well, we can't leave it in the room,
Right.
but we can put it in the fridge. or
I mean,
whatever.
like it's gonna be
It
gone
was
like
empty
by
for a
the end
month.
of tomorrow.
Yeah, no. I mean, it'd be fine, but.
I can
but-
carry this to the fridge or whatever, and put a stone.
Yeah, it's just, they wouldn't be okay with us leaving it here even if that was our plan, like,
Okay.
we could make that our plan, but that would involve us putting.
Sure, like, you want to take them.
Through there. Somebody picking that.
Maybe this one. The full box.
The full one?
Yeah, it was like a vegan one that nobody wants.
Has
Which was your name, by the way?
Christoph.
Christoph
That one
Silas.
has meat,
Silas,
and
nice
it
to
also
meet you.
has like the.
Oh, yeah, make sure to get on Zulip if you haven't.
Oh, yeah.
I'll take it, no one else does, but unless you think you're gonna eat here.
Oh, well, maybe, I don't know.
I'll take it.
Yeah.
But, where should we put the
Yeah, where's the refrigerator at or wherever?
Liquid up here.
I can get us into the fridge.
Alright.
I'm coming back here, right? We're coming back here, right? Oh, do you want? I think there is, another one on top of mine, I don't know if it'll fall off. Oh, you don't want to, you see that?
I'm gonna make sure all good on good.
got stuff
Okay.
in the fridge, so I'll help you carry whatever.
We just need to make sure everything's in here. That one's nice.
Oh, yeah.